And now we move on to the examples part of our discussion on optics. I have decided to divide the discussion of the examples part into two parts. In this video, we'll cover the first part rather, and then in the next video, we'll cover the second part of the examples. Consider now the following example. Example 1. When a rectangular metal tank, as shown in the figure, is filled with an unknown liquid up to the top of the tank, with the level of the top of the tank with eye level with level with the eye of an observer as shown, the observer can just see the opposite corner F of the tank. Determine the index of refraction of the liquid. So you have a tank filled with liquid at level with the top of the tank, and top of the liquid is the eyes of the observer, and the observer can see the corner F basically in line with this corner of the tank. With that information, as well as the information that the depth of the tank is 0.6 meters and the length of the tank is 1 meter, with this information, determine the index of refraction of this unknown liquid. So what happens is, light from the bottom corner F will travel towards the opposite corner and then go from the liquid to the air. The light will refract until it reaches the eyes of the observer. And the observer is thus able to see the bottom corner F. So here we have refraction of light from one medium to the other, from the unknown liquid to the air. The unknown liquid will be our medium 1 and air will be the medium 2. So N2, index of refraction of air, we know to be 1.0. Let D be the depth of the tank, 0.6 meters, and L be the length of the tank, 1 meter. Medium 1, medium 2, N1, N2, this is the interface between the two media, and the normal line to the interface is this line. We get our angle of incidence, theta 1, and angle of refraction, theta 2. From the figure, we can easily see that the angle of refraction, theta 2, is 90 degrees. We know the length adjacent to theta 1, depth D, and opposite theta 1 is the length L. Using our SOHCAHTOA, using tangent function, we are able to calculate the angle of incidence theta 1. Tangent theta 1 is L over D, getting the inverse tangent, or we know L rather, and D, so opposite over adjacent. So opposite over adjacent, we are able to get theta 1 to be 59.03624,347 degrees. And then using the law of refraction, N1 sine theta 1 is equal to N2 sine theta 2. The only unknown is N1, index of refraction of the unknown liquid. So isolating and plotting in the values that we know into the equation, we are able to calculate the index of refraction N1, the index of refraction of the unknown liquid. N1 is equal to 1.166. Next up, we have example number 2. In the figure shown, a ray of light is incident on this face of a glass prism. On the face AB, the index of refraction of the glass prism is given to be 1.81. Determine the maximum value of the angle phi, the maximum value that this angle can have, so that the ray of light will be totally reflected when it strikes the face AC of the prism when the prism is immersed in water. So again, we have two media, the prism and then the surrounding water. We have N1 and N2. Let N1 be the prism, 1.81, and N2 be the water surrounding the prism. And we know the index of refraction of water to be 1.33. When light encounters an interface and the light is perpendicular to the interface, the law of refraction will simply tell you that the light will continue on straight into the other medium. So no change or no bending of light, no change in the orientation or direction of the light when it passes from this medium to into the prism, because the incident light is perpendicular to the interface. And I'll leave it up to you to verify that. Use this situation and test out the law of refraction, and you will see that the refracted light will also be perpendicular to the interface. Once inside the prism, the light will continue on until it strikes the face AC of the prism. And the problem tells us what should be angle phi such that instead of passing through the interface, the light will be totally reflected. This situation, you will recall, is known as total internal reflection, wherein the angle of incidence, so get the normal line, the line normal to the face AC, you have angle of incidence theta 1, wherein theta 1, for total internal reflection to happen, theta 1 must be equal to the critical angle. So theta 1 must be the critical angle. Using our equation for total internal reflection, theta c is equal to inverse sine of n2 over n1. Knowing n2, knowing n1, we are able to calculate theta 1, 47.2908791 degrees. Total internal reflection can happen because n1 is greater than n2. One of the conditions, you will recall, one of the conditions for total internal reflection to happen. N1 must be greater than N2. And the fact that we got an answer for theta 1 for the critical angle, that means total internal reflection is indeed possible for this situation, for the system described by the problem. Phi, bisecting lines, this is also angle phi, phi, and then the other angle is theta 1. Phi plus theta 1 is equal to 90 degrees according to our figure. Therefore, phi is just 90 minus theta 1. And knowing theta 1, we are now able to calculate the angle phi. 42.709 degrees. So that's it for now. We'll continue our discussion of the examples part in the next video. Example part 2. So thank you for watching.